earlier classes we had seen error due to input resistance, error due to the output resistance, and then offset voltage drift, bias current drift, and so on. Now, let us see how to calculate these errors in a bird's eye view. So, we will see the calculation of various errors, calculations of op amp errors. So, we will take different circuits and see how these errors are appearing, how to compute these errors in given circuit. So, let us take for example, our voltage regulator start with. We had this transformer and then we had a rectifier, then we get a DC voltage. And if we see our regulator circuit, so we had this operation amplifier, then the error amplifier gets a reference voltage through the reference Zener. So, we connect this, then this. So, this is a voltage regulator and this is the output voltage. So, if these resistance are equal and if this is a 5 volt, then the regulator output voltage is 10 volt. So, if we see the V output actually comes as 5 volt into 2, that actually comes as the 10 volt. Now, what is the temperature drift error in this circuit? Let us assume I have put here 100 k and 100 k, these two resistors 100 k, 100 k. Now, the base emitter voltage drift of these transistors are not a issue, because this is in a closed loop. So, if we take this circuit, that you have a 5 volt here and any change at the output is compared at this point with respect to 5 volt. If the voltage goes up above 5, then automatically this voltage comes down and the output also comes down. So, base emitter voltage drift of these two transistors, say T1 and T2, if I take T1 and T2, base VBE drift of T1 and D2, VBE drift of T1 and T2 is actually compensated by the loop gain. The loop gain in this case is actually open loop gain of the op amp divided by 2. So, since the loop gain is very large, the drift of D1 by D2 has negligible effect on the circuit, because this is the closed loop, whereas offset voltage drift of the op amp is it will directly affect the output. So, offset voltage drift, V offset drift of op amp directly affects the output. For example, if I use 741, in that case the offset voltage drift would be 15 microvolt per degree C. For 741 drift is equal to 15 microvolt per degree C. For 100 degree C temperature change, this comes 1.5 millivolt. So, 1.5 millivolt drift at the input, 1.5 millivolt drift comes 1.5 millivolt drift comes at this point. Now, that is equivalent telling 3 millivolt drift at the output. So, it will produce a 3 millivolt drift at the output. So, total drift at the output would be, so total drift drift is 3 millivolt at the output. This is due to offset voltage drift. Similarly, if you see this circuit, the Zener drift, Zener also drifts. So, Zener drift directly affect the output. If Zener is 30 ppm Zener, then for 30 Zener, next we can see the Zener drift. Zener drift error. If you look at the spec of the Zener, for example, if it is LM 336, drift is actually drift spec is 30 ppm per degree C. So, for 100 degree C, drift would be 30 into 100 divided by 10 power 6 into 5 volt, that actually comes 150 into 10 power 2 divided by 10 power 6, that turns out to be 150 into 10 power minus 4, that is 15 millivolt. So, the expected output drift is the expected output drift is 30 millivolt. Similarly, we will have a drift due to due to this resistance, because the resistance change will also produce drift, and the bias current change also will add the drift. The resistance change we already calculated. If we use, for example, 10 ppm resistance, 25 ppm resistance, then we have to take one is increasing, another one is decreasing, and then accordingly we have to find out what is the output voltage drift. Then similarly, the bias current that is flowing through that will have a error, because there is no equivalent resistance in the plus side, because this bias current whatever is flowing through this have to go through this. The bias current actually have to go through this. So, the bias current when drifts, then the current flowing through this is changing, consequently voltage across this changing, and output also will have a effect. So, for that keep this resistance lower, instead of 100 k, keep this resistance lower, then you will have a less drift due to bias current. Similarly, so we have the other error is bias current drift, resistance, that is resistance drift error. So, we have third one, resistance drift error, and then the fourth one is bias current drift error. Bias current, this is only R1 and R2 matters. Bias current drift error, here again R1 and R2 only matters, because if you take the other resistors, that is if you take the other resistors, for example, in this case this resistance is there, this resistance has no effect even if this drifts. So, the R1 R2 drift matters, and then the bias current that is flowing through this actually is not compensated, that actually creates problem because of R1. If I want to reduce the error, then I add another resistance here. So, that both have same bias current and same R I can put here. So, that reduce the bias current error. I am not calculating here the bias current error, but the bias current error contributed by this, reduce the bias current error by adding a reduce the bias current error by reducing the R1 and R2, that is R1 and R2, or alternatively or add resistance in the non-inverting non inverting input. So, this is the error that comes in the voltage regulator. Let us see some other circuit, how to compute the error in other circuit, like take for example, current sensing. So, assume that we are having a H bridge switching, and then we want limit the short circuit current, like take for example, we take the second circuit, circuit 2, H bridge drive. Current, we will calculate the current sensing error. Current sensing error. In this case, what we are trying to achieve is that assume that we have a H bridge, a MOSFET based. We have T1, T2, and then T3 and T4. There are 4 switches and the load is connected here. So, this is the supply here. Now, if you want to provide a short circuit protection, then normally what is done is we will add the resistance. So, I will expand this little bit in the ground side. So, what you do is that I will add the resistance here, and I will add the resistance here. Now, this I connect it to ground. Now, for short circuit protection, what I do is I will add the current, that is I will add the resistance here. For example, I will put on transistor, connect to this to ground, then I connect the resistance here. So, assume that we have a pulse coming at this point, then what is normally done is that you switch on the giving a pulse to this. So, it switches on and then make it off by connecting this. So, in this case, when the plus 15 volt is given here, the plus 15 volt actually is applied to the gate, and then the gate actually turns on the MOSFET, the current actually flows through this. So, we have this sense resistance R here. So, this is the sense resistance, and current flowing through that produces a voltage at this point. So, when similarly when they turn this one to 0, then since this is 0 and this is already charged to plus 15, and this transistor conducts and discharges it, that way that MOSFET is switched on and off. In case of the short circuit of the load, or if this transistor turned on when it is supposed to be off, for example, when this is on, this transistor should be when this is on, this should be off, but when this is on, if this comes on for some reason, or if the resistance is shorted, then high current flows through that. We want to protect this from the damage. So, we have done we have put a sense resistance, voltage across this is applied to this. So, when the voltage at this point goes more than 0.6, then this transistor will conduct. So, I can connect this here, but if I connect like this, the problem is that this will be limited to 0.6 and the conduction will take place. Assume that I have a small resistance here. So, the voltage drops such that always 0.6 goes, 0.6 is at this point, you will have 0.6 at this point, and then this transistor T2 will be taken to a linear region. So, by this is a conventional linear regulator current limiter. In this circuit will limit the current, but it will damage the T2 because of heating. So, we had to latch the pulse. So, that is to be done. So, we can add a latching circuit to the above. So, what we can do is I redraw this last part alone. So, we have the MOSFET and then we have a sense resistance here. Now, what can be done is that we can have a sense resistance and then that is connected to this. So, if the voltage at this, if the current goes high, then voltage across this voltage at this point increases, and that will make this transistor to conduct. Now, what you do is to make this transistor latch the pulse, that is incoming pulse. What you do is we will have, for example, we have a circuit like this. Assume we have a resistance here. So, what can be done is we can have a latch part that can be designed this way. We will have the and then this can be connected to this. So, essentially I will name it now R1, you have R2 and this is R3, this is the incoming pulse that is coming here, and this is R4, R5, R6, and then we have our okay, we will have this input pulse, and then we will have a regular switching off mechanism that is there here. So, we will have transistor say T1 or T5. So, transistor T5, this is T6, we put it as T7. So, when pulse comes on here, that turns on the device and the current flows through this. So, we are trying to make a provide a short circuit protection. So, the large current that is flowing through this will develop a voltage here, and that voltage appears here, and that once it goes more than 0.6, then transistor T6 conducts. Conducts. Once transistor T6 conducts, then the voltage across R1 once exceeds more than 0.6, then T7 will conduct, and that voltage will appear at this point. That will make this T6 to go on continuously, and then the heavy current that is flowing here will make this voltage to drop, and the transistor will go off. But once it goes off, it continue to be off because this voltage whatever is there, that will be continuously driving this transistor and make the current to latch actually. So, essentially this is for short circuit protection. So, T6 is the one which senses the current. So, the T6, that is voltage across R4. So, if I take this, so voltage across R4 is applied to T6. So, at base when voltage is more than 0.6, when the voltage at this point is more than 0.6, then that makes the current flow R1, and T7 is turned on, and then voltage applied back to T6. So, applied to T6 when the voltage is when T6 VBE is greater than 0.6 volt, T6 is turned on, T6 turned on. This makes T7 to turn on, because then T6 is turned on. Once T6 is turned on, then T7 will be turned on once the voltage across R1 goes above 0.6. This makes T7 to turn on. Then once T7 turn on, T6 get latched. This makes T7 to turn on. This makes voltage at the base of T6 to be present even without the current. That is T6 is latched. T6 is latched. That means transistor, that is our power transistor, that is this one, that is T. I think this power transistor named as T2. So, the power MOSFET power transistor T2 will be off. This makes T2 to go off. This makes T2 to go off. This latch will continue up to the next pulse. When the next pulse comes, or when the pulse input tend to 0, then the latch is read, because there is no current will flow through T7, and then the latch will be reset. That is, once current exceeds this makes T2 to go off. So, T2 will be off for the remaining period of the pulse. The latch will be reset. The latch will be reset at the next latch will be reset at the next 0 pulse input. Now, in this case, what is the drift? Because we have taken that 0.6, it will be reset. So, if I take, for example, R5 and R6 are equal, then if this voltage is 1.2 volt, assume that this voltage is 1.2 volt, then the T6 base will be 0.6. That means, the latching operation will be initiated at 1.2 volt. Suppose if it is 1 ohm resistance, if R4 is 1 ohm. So, if I take R4 as 1 ohm, if R4 is equal to 1 ohm, then at 1.2 ampere current 0.6 volt will appear at the base of T6. That means, at 1.2 ampere latching will take place. So, current limiting is taking place at 1.6 ampere. Current limiting is taking place at 1.2 ampere. But when this will happen at 25 degrees C ambient, because at 25 degrees ambient only at 0.6 actually the transistor T6 conducts, because when the voltage is 0.6 at this point, the transistor T6 conducts, but when the temperature of this device goes up, say at 80 degree, then it needs a much lower voltage, because 2.2 millivolt per degree C. So, at 50 degree you will lose 100 millivolt, that means at 0.5 volt only, at 0.5 itself T6 will be conducting when the temperature of this is at 80 degree. That means 0.5 we need, means we need 1 volt here. That means at 75 degree, at 80 degree we need roughly current limiting will take place only at 1 amps. That means this is at this is at 25 degree C ambient. At 75 degree C ambient, then T6 needs only 0.5 volt. So, current limiting will take place. So, current limiting will take place at 1 amps. So, obviously with the temperature the current limiting is changing. So, we want to avoid this. So, how will you modify this current limiting, the drift that is occurring due to T6, because base emitter voltage drift now affects the current limiting. Now, the circuit can be modified in the following manner to compensate for the temperature drift. For example, the trick that was used in the op amp can be used again here to remove the base emitter voltage drift in this case. So, we can redraw the circuit, that is, we can have the switching transistor here and with the resistance. Now, what can be done is that this can be applied in the similar manner to the transistor here, and then we can also apply this, and here we can have a V reference. Then the latch function can be retained as it is. So, what we can do is we can have the this, and to this transistor the latch function can be added. So, we can have a device here, and this can be connected to this, and then the output of this can be connected to this. This can be even connected to supply. So, in this case the temperature drift that was affecting the current limiting function can be removed by adding this additional transistor. That is, we have added now this transistor to compensate the VBE drift of this, because in this case if the current goes high, then voltage at this point will go high, and then voltage at this point will go high, then this will be start conducting. But then we had kept this one at reference voltage, because this is connected to V, say plus supply, and assume that we had kept this one at 1.2 volt Zener. If it is at 1.2 volt Zener, then this will be start conducting only when it is above 1.2 volt, otherwise it will not conduct, because if assume that room temperature it is 0.6 volt is the drop, then this will be sitting at 0.6 volt, and this will start conducting only above 1.2 volt. So, above 1.2 volt this transistor will be conducting, that when this transistor conducts the current will flow through this, that is above 1.2 the conduction will take place through this. Once it conducts, then this voltage will come, and this voltage will come permanently high and make the produce the latching function actually, and this can be given for the drive. Of course, we also have to add the reset function here, that can be done in the regular manner. So, this reset function can be provided in a regular manner. So, once this voltage goes above 2.4, then this will go above 1.2. then this will be conducting, and then this function will be current will be latched, and then the transistor will be turned off fully up to the next pulse. When the next pulse when the pulse goes to 0, and this this latch will reset, and then it is ready for next short circuit protection. By incorporating this transistor, we are avoided the drift produced by this base emitter voltage. So, we will call this one as T8, and then this we have named it earlier, we have named it as T6. So, we will put it this as T6. So, we have this is T6. So, by adding T8 and the V reference voltage, we are avoided the drift of the base emitter voltage drift of the T6. So, what is done is base emitter or VBE drift of T6 is eliminated by using T8 and V reference. Now, because for example, if the temperature changes, suppose if the temperature goes high, then we need only 0.5 volt difference here, 0.5 volt difference only needed, and since this also needs only 0.5 volt, but at higher temperature instead of 0.6, then this will shift to 0.7. For example, at high temperature this will shift to 0.7 because it needs only 0.5. So, this will stay at 0.7, and again this also needs only 0.5 volt. So, again it will at high temperature also it will limit at only at 1.2 volt. So, if temperature drift has no effect on the current limiting. This is because when VBE changes, I will call this resistance as R10. Voltage across R10 also changes, the voltage across R10 also changes. For example, at 25 degree C, voltage across R10 is actually 0.6 volt. At 75 degree it comes nearly to 0.5 volt. Because now base emitter voltage had decreased, and the base emitter voltage had decreased. So, at high temperature it only becoming it had become 0.7. Now, the T6 also needs only 0.5 volt. So, T6 for example, now T6 conducts at 25 degree ambient when VBE is 0.6 volt, that is voltage at the base is 0.6 plus 0.6, that is 1.2 volt. Then same thing, T6 conducts at 75 degree C ambient when VBE is 0.5 volt, that is voltage at the base is 0.5 plus 0.7, that is equal to 1.2 volt again. So, all the time it limits the current only at 1.2 volt, that is at all temperatures current limiting is taking place, current limiting is taking place when T6 base voltage is at 1.2 volt. So, the drift has no effect in this case. This is how in the operation amplifier also the drift was cancelled, which we already discussed. So, we can compensate the current drift of the transistor in this way. Let us see another circuit wherein op amp is used and how the drift is calculated. Take the example circuit 3. So, I will take next example circuit 3. In this case we take a proportional temperature controller and we use sensor as a thermocouple. So, thermocouple based proportional temperature controller we take in this example, thermocouple based proportional temperature controller. Let us calculate the drift. So, drift calculation. So, take the input stage that we have a thermocouple and thermocouple amplifier is there. Assume that we have an amplifier like this. Gain of 25, that is 24K and 1K. So, thermocouple gives 40 microvolt per degree C, and that makes 1 millivolt per degree C sensitivity at the output, because the gain is 25 and when it is amplified by 25 times the signal becomes 1 millivolt. Now, we want to make a proportional controller. So, we will find the difference between the reference voltage and the actual temperature. So, we have a reference amplifier here which has set temperature. That is a V reference. So, this is a V reference, say 5 volt, and we set whatever voltage that is required. So, we have A and B. So, A gives you the actual temperature and then A gives you actual temperature, B is the set temperature, and then if I put for example, the values are equal, and then I will have error voltage. So, that which is nothing but difference between A minus B or B minus A is what it is coming at this point. So, that is called error voltage. So, A is actually the actual temperature, the point A gives you the actual temperature, gives the actual temperature. Point B gives you point B gives you reference temperature, that is set temperature. B minus A error voltage. There is a difference between the two, say the difference between set value and the actual temperature is coming as error voltage. This error voltage is amplified and given to the heater to make it as a controller. So, normally what is done is this output is given to the next stage. So, the next stage consists of an amplifier, so the output of that is given to this, then this is given driven in the heater. For example, I can have a heater circuit here. This is a heater and the sensor is linked to this directly. Physically the sensor is linked to the heater. So, this forms a complete proportional controller. So, if we have here plus input, so this is the gain stage for proportional controller. Gain is set by these two resistance. So, this forms a complete proportional controller. Now, let us try to find what are the errors associated in this circuit. Now, if we say the stage 1, that is I will take that as op amp 1, this is op amp 2 and then op amp 3. Now, the stage 1 handles the lowest signal, that is a 40 microvolt input is actually applied to the input. So, this would give us that offset voltage drift of the op amp 1 is a serious concern. So, now we will continue to write the functioning of the circuit, that B minus A gives error voltage, then the op amp the 3 amplifies the error voltage. So, I write the op amp 3 amplifies the error voltage, error voltage and the amplified voltage is applied to the heater, through the transistors. Transistor mainly used for the current boosting. So, basically the error voltage at this point what is coming is amplified and applied to the heater. Now, we will see the errors. So, the op amp 1 handles the very low level signal. So, op amp 1 so we calculate the errors. So, we will now calculate the calculation of errors. On the operational amplifier 1 handles the lowest voltage, handles the low level signal. So, the offset voltage drift of this op amp is very important, because op amp 1 sees the lowest voltage. So, offset voltage drift of the op amp is a matter of concern. So, the op amp the offset low level, so offset voltage drift of op amp 1 is a concern, because here we should use low offset voltage drift op amp, because otherwise whatever drift, for example, if I use 741 in this case, which has 15 microvolt per degree offset voltage drift, for 100 degree then it will be 1.5 millivolt. 1.5 millivolt drift at the input will correspond to if we calculate 1.5 millivolt, that is 1500 divided by 40, that comes 37.5 degree error. So, this should have a very low offset voltage drift. So, use low offset voltage drift op amp for op amp 1. So, use low offset voltage drift op amp. For example, if I use LM07 V offset drift is 0.5 microvolt per degree C. So, that will give for 100 degree 50 microvolt, for 100 degree ambient temperature change, 50 microvolt drift is expected. 50 microvolt drift is expected. This is equivalent to equal to 50 divided by 40, that is 1.25 degree error. So, you have to use the low offset voltage drift op amp for op amp 1, otherwise there will be a large error. Similarly, these resistors what we have used are actually 24K and 1K, and if I use very high resistance, then I have to use bias current error also. Of course, it is better to add here one resistance roughly 1K, so that the most of the bias current flowing here and equal to here, that will be get compensated. There is this parallel combination of these two should be utilized, and then keep this RF and R1, keep this RF and R1 lower value, so that even offset voltage drift is lower. Of course, in this case input impedance is not a serious problem, because the thermocouple has very low internal resistance. So, input impedance error is not much. So, in this case if we consider only offset voltage drift and the bias current drift itself, it is enough. More importantly, in such a low level signal when you are handling, it is the offset voltage drift that is to be considered very often. Then if you look at the second stage, that is op amp 2. In the op amp 2, the signal level is already 1 millivolt. So, the drift of the most of the op amp is not more than 15 microvolt per degree C. So, even for 100 degree it is only 1.5 millivolt, that will correspond to only 1.5 degree error at this point. So, this need not be a very low offset voltage drift op amp, because very low offset voltage drift op amps cost more. So, at this stage need not have very high offset voltage, very low offset voltage drift op amp, not necessary for this. The difference only is amplified here. Of course, the resistance values used should not be very high. So, for example, I need not put very high value. So, this value is to be 10K to be used. One thing, that if these resistance are not matched, which we had discussed earlier when we were discussing about the constant current sources, if the resistance are not matched, say if they are 10Ks, but they may have 1% error if I use 1% resistance, and they may have a 10% error if I use a 10% tolerance resistance, but then that will act as a common mode error. So, this resistance must have at least 1% error or better to avoid the common mode voltage, because when we are varying this, then this voltage also latches up to the same value when the loop is balanced. So, when we are changing this per set at different temperature, then the common mode error will come in. So, here the op amp is not a serious issue, selection of the resistance is a matter of concern here. Similarly, if you look at the op amp 3, in op amp 3 the signal is already 1 millivolt per degree C. So, this also need not have very high this need not be very low drift op amp, because even if I use ordinary op amp which is having 1.5 millivolt drift for 100 degree C, the error will be only 1.5 degree. So, but if the error need to be kept very low, then one option is use go for say 50 gain. For example, if I use a 50 gain here and if I use a low offset voltage, then this stage and this stage error will be small. Of course, keeping this resistance small helps a lot reducing the offset voltage drift. Now, the base emitter voltage drift of this and base emitter voltage of this transistors is not a concern, because they are compensated in the closed loop and the error is reduced because of the loop gain. So, for example, if this is a 15 volt, say T1 T2, the base emitter voltage drift of T1 T2 is not a serious problem. So, for example, if I use first stage as upper one as a first stage and the if I use 25 gain, if I use 25 gain, then total error due to offset voltage drift can be calculated. So, we calculate total error due to offset voltage drift. Stage 1 op amp 1. Here the offset voltage drift error comes 1.5 say 0.5 millivolt operation op amp were used. So, total drift is 50 microvolt divided by 40 microvolt per degree C, that comes 1.25 degree. Op amp 2, if I use op amp 2 normal op amp. So, the total offset voltage drift is comes out to be 1.5 millivolt per 100 degree C. So, error in this stage would be turns out to be 1.5 millivolt is error and signal is actually at this stage 1 millivolt is a signal per degree C. Signal, because 40 microvolt amplified by 25 times gives you 1 millivolt. So, that comes out 1.5. So, op amp second stage error will be 1.5 degree C. Third stage op amp 3, error in the op amp stage 3. Op amp 3 error, that works out to be the total drift again here is 1.5 millivolt and the signal is 1 millivolt, again it is 1 millivolt. So, that comes 1.5 degree C. So, total error will be 1.25 plus 1.5 plus 1.5. So, the total offset drift alone comes to be 4.25 degree. If I use first stage as low drift op amp, that is 0.5 microvolt per degree drift error op amp, and the two other stages are 1 millivolt, other stages are normal op amp, which is 15 microvolt per degree C op amps. So, one can reduce this error by increasing the gain. If gain in the first stage is increased, if gain in op amp 1 is kept as 50, then the error comes down. In this case, op amp 1 error would be will remain, that will be 1.25 degree C. The op amp 2 error will be error would be now same 1.5 millivolt. Now, the signal is 2 millivolt. So, this will actually become 3 by 4th 0.75 degree error. The op amp 3 error would be error would be again same 1.5 millivolt by 2 millivolt, that is again 0.75 degree. So, total error becomes actually it becomes 1.25 plus 0.75 and 0.75 that comes 2.75 degree. So, one can reduce the total error due to offset voltage by increasing the gain of the first stage. So, one can closely calculate the error in each stage and then see that the circuit functions with least error. This is the most critical thing in analog circuit design, that is the error budgeting. Error budgeting is an important issue in analog circuit, and then error compensation is another important issue that also we had shown in our second circuit example. So, with this I will close this today's lecture. We will see the other issues in the next class. Thank you.